Now that we've studied experiment, sample space, and events, we are ready to talk about probability. So let's begin. What is probability? In the simplest word, probability means how likely something is to happen. Okay? So it is actually an extent in a form of numerical description of numerical description to which an event is likely to occur. All right, and it's measured by the ratio of the favorable cases to the whole number of possible cases. All right, so this is probability. It's a numerical form of an extent that says how likely something is to occur. All right, we've even using it from a time when we didn't know about it. Do you know that? Like when watching a cricket match or taking part in it, we start with a toss to decide who will bat first, who will bowl first, right? So we'd say that the chance of winning for any of the two teams taking part in this toss is 50-50. Indeed, this 50-50 stands for the percentage that says that each of the team has got 50% chance to win. But how did we come to this conclusion? Here's the logic behind. For a coin, when flipped, there are two results possible, right? All right. So the results are head and tail. Okay, these two. So if someone calls a head, that means his expected event, say it's E, equals to this set. He's expecting a head, that's why he called it, and his expected event has H in it, and let's call the event E. But the sample space, say it's omega, has two elements in it, right? H comma T. Then what we actually do is, for determining the probability of E, that means the probability of head to show up equals to the number of element in A divided by the number of element in sample space, which is half. So when this half is converted to 50, so converted to percentage, we get 50%. So that's why we say that it's 50-50 chance. So in general, probability of an event happening, sorry, probability of an event happening equals the number of ways something can happen divided by the total number of outcomes, right? So it's actually the number of favorable cases, right? So the number of favorable cases divided by total number of outcomes. Note that the numerator of this fraction is actually the cardinality of the event, right, that we are expecting to happen, and the denominator is denoting the cardinality of the sample space. All right, let's see an example. Okay, so the question is, what is the probability of rolling a 3 with a die? You are rolling one die and you want a 3. What is the probability of getting a 3? That's a question. So according to our formula, we can say that this is the solution. First, we have to determine the number of ways it can happen. So that means the number of ways a 3 can show up from a die. So there's only one way, because what? Because there is only one face with a 3 on it, right? There's only one face of the die that has a 3 written on it, so only one way it can happen. And again, the total number of outcomes or total number of results, so it will be 6 definitely, because there are 6 faces all together and all the sides are equally likely to come, right? So there are 6 possibilities. Therefore, the probability equals to 1 by 6. All right. So if we want to determine the probability of an event, then we have to follow these following steps. The steps, or step by step, finding the probability. What are the steps? Yeah. So step 1 will be to find event A. What is event A? The event whose probability has to be determined. So we actually have to determine the event with the favorable outcomes. Then step 2, calculate cardinality of A. So this means the size of A, or the number of outcomes as elements in set A or event A. We know that event is a set. And 3 is dividing cardinality of A by cardinality of the sample space. This is total number of outcomes. So these are the 3 steps to follow when determining the probability of some event. Let's see another example. Okay. Okay, let's example. The question here is, what is the probability of rolling an even number with a die? Pretty much similar with the last example. So we asked, if a die is rolled, what is the probability that it will show an even number? Okay. Yeah. So the first step for us will be determining the event. So solution, say A is the event rolling an even number. Okay, rolling an even number is called event A. So how many elements are there in this event? We know that event is a set and it is comprised of all the outcomes that satisfy this condition, right? So 2 is an even number, 4 is an even number, and 6. So A will have 3 elements in it. So 2, 4, 6. This is step 1. Now step 2 is to find the cardinality of event A. So modulus A equals to 3. Step 3 is to determine the cardinality of the sample space of this experiment and dividing mod A by mod omega, right? So the sample space here will have 6 elements in it. All the possible outcomes needs to be enlisted in this set, and then cardinality equals to 6. Therefore, so the probability of rolling an even number equals to P of A equals to cardinality A by cardinality omega, so 3 by 6, which is half. All right, I hope you understand it. Let's see another example. It's pretty easy. So the statement is there's a box and there are 5 balls in it. 4 of them are yellow, 1 is blue. So the question is, if you choose a ball at random from this box, what is the probability that it will be yellow? Alright, so that's a statement. The answer is 4 by 5, and it's really easy to solve. I hope you can do it by yourself. So these examples, in those examples we've solved, we've seen that while flipping a coin, if we want a head, then the probability is half, right? Here H denotes the event of getting a head from one flip. Similarly, the probability of rolling a 3 with a die, let's call it D3, the event D3. So the probability of it is 1 by 6, and in the latest problem, if you choose 1 out of 4 yellow balls from a 5 balls box, is 4 by 5. Alright, so yeah, Y denotes the event of picking a yellow ball at random. So now you see that probability is a function that assigns a real number to each of the events. Okay, like it assigned half to event H, 1 by 6 to D3, and 4 by 5 to Y. Therefore we can say that probability is a function. Probability is a function that assigns real number to events. Alright, so during this assignment it follows a few axioms. So let's know the axioms that are followed by probability function axioms. So we are going to state them first. For any event A, P of A is less or equals to 1, greater or equals to 0. Right? 2. For any sample space of an experiment, P of omega equals to 1. And 3. For any two disjoint events, we're gonna know what disjoint events are later. Say they are A and B. The probability of either of these events to happen is the sum of the separate probabilities. Okay, so these are the 3 axioms that are usually followed by probability function. Let's talk about them individually. So our axiom 1. The axiom 1 says for any event A, the probability should always be less or equals to 1, greater or equals to 0. And why is it so? From the definition of event, we know that any event A is a subset of the sample space. Alright? So since it's a set, the number of elements in it can be at least 0, right? So the least number of elements that A might have is 0, because no set can have negative number of elements, right? You can say that I have minus 50 students in my class, or I am minus 18 years old, or there are minus 2 apples in the box. So there are some figures that cannot be negative. So the cardinality of any set A, in this case it's an event, should be greater or equals to 0. And since it's a subset of the sample space, so all the outcomes in event A already exist in the sample space. Therefore, the number of elements in the sample space should be less or equals to the number of element in the event should be less or equals to the number of element of sample space. All right, so yeah, this is true. And now we are going to divide this inequality by the cardinality of sample space. So you will get this. By definition, we have probability of A here. P of A, and it's less or equals to 1, greater or equals to 0, because when 0 is divided by anything, the answer is 0. And here note that the cardinality of sample space, which is this modulus omega, it cannot be 0. All right, it must be a positive figure. That is why when it's dividing 0, it gives 0 as a result. All right, so and yeah, it cannot be negative as well. That's why the direction of the inequality signs are preserved. So yeah, we have proved the axiom 1. Now let's try to realize what these inequality actually mean from the Venn diagram. So in figure 2, we are trying to represent a sample space of the experiment of rolling a die with a rectangle. So it has all the outcomes in it, 1 2 3 4 5 6, in form of smaller sets or smaller events like rectangular cells. So we were interested in getting 3. Okay, so the probability of rolling a 3 actually represents the fraction of the area of the sample space covered by the event of my interest. All right, you see that this green region with 3 is actually 1/6 of the total area of the sample space. Therefore, it's around 17%, and we've written that the probability is 1/6. All right, so if we try to improve this area of this region, then the probability increases. We are going big, so the maximum area that an event can cover will be the area equal to the sample space. Mind it, the event cannot cross the boundary of the sample space since it's by definition a subset. Okay, so when it has covered the whole sample space, then what is the fraction it covered? The fraction is 1. In other words, it can be expressed as 100%. all right, so this is the maximum probability of any event that can reach, which is 1, with the right side of our inequality here. And if we try to decrease the area of the event, then it reaches the cell's area, and when it's even smaller, the fraction gets smaller, and it can become 0. But there's no way the fraction can be negative. All right, so this actually explains the left side of our inequality. I hope you understand it now. So look at figure 3, where we have tried to show the Venn diagram for the experiment of flipping a coin. Here the H with the red region, it covers 50% of the area. That is why the probability is half. It's also within the bound of 0 to 1. And similarly, in our latest problem, we saw that picking one of the 4 yellow balls out of 5 in total has a probability of 4 by 5, which is 80%. So this yellow region is 80% of the total area, which is the fraction of the sample space. So yeah, that's it. We are pretty much done with our axiom 1. Okay, now let's move to axiom 2. This axiom can be directly deduced from the definition of probability. So by definition, we know that P of omega should be equals to the number of element in the event of interest, which is omega here, divided by number of element in the sample space. So it becomes 1. That is why we can write it like P of omega equals to 1. If we want to see this problem from the perspective of Venn diagram, then we can say that by P of omega, we actually ask what fraction of the area of the sample space is covered by the event of sample space. Okay, so it's 100% because both of the sets are same. That's why we can say that P of omega equals to 1.